Okay, so now we're going to get into a discussion of wave functions. And this is the area in physics and chemistry which is known as quantum mechanics. Basically, quantum mechanics is a treatment of the atomic structure through the wave-like properties that are displayed by electrons. And the person who came up with this whole approach is what you see on the screen right here. His name is Erwin Schrödinger. He developed an equation which basically describes behavior of the electron in the hydrogen based on the wave-like properties of the electron. The wave function, by definition, is a solution to this equation, and it represents the energy state of the atom. So basically, the wave mechanic approach gives the probability of finding the electron within a certain region of an atom. And the Born interpretation, Born is another physicist who was working on this issue at the time, he said that the square of the wave function, which is represented by psi, so psi squared, gives the probability of finding an electron in a small volume of space around the atom. So this basically deviates from the Bohr model, because the Bohr model talks about the electrons located within certain orbits, certain energy levels. Basically what the Bohr approach is, along with the Schrödinger approach, it leads to an idea of an electron density. So basically the electron will be located in a region of space, and therefore you cannot really pinpoint the electron being at a particular location at a particular point in time. In fact, this guy, Werner Heisenberg, he came up with what is now known as the uncertainty principle, which states that we cannot simultaneously know exactly where a particle like an electron and exactly how it is moving. All right, so, and the reason why that is so is because the act of measuring the particle's location actually interferes with the particle. So to illustrate this, let's say we have a photon, or I should say an electron, and let's say this microscope is designed so that it can see the electron, but the only way it can see the electron is if the photon hits the electron and reflects off it and heads towards the microscope. The problem is that by the time the microscope detects the photon, which indicates where the photon was, the photon would have been affected by the electron would be affected by the photon and be already dislocated from its original position. So therefore, that's the reason why the uncertainty principle holds. Basically what the uncertainty principle says in this particular example is that at the time when you see the electron, its location, the photon would have displaced it so that you would have thought you would have seen it at that instance, but the electron would be elsewhere. It says in light of the uncertainty principle, the Bohr model fails for the hydrogen atom, because the hydrogen atom Bohr model basically indicates that electrons are located within orbits, and that is certainly not what the uncertainty principle predicts. So that leads us to a discussion of the quantum numbers. Now, the wave functions that were discussed earlier contain three parameters. Now, fortunately for you guys, you don't need to know all the details about the wave functions. What we're going to get into are basically quantum numbers that are needed to solve these wave functions, and these quantum numbers have specific rules. Any wave function with a given set of these quantum numbers is called an atomic orbital, and these orbitals allow us to visualize the region in space where there's a probability of finding an electron. So the first quantum number we're going to talk about is what is known as a principal quantum number, and the symbol that is used to represent the principal quantum number is the letter n, and it's usually a lowercase n and not an uppercase n. Now, this principal quantum number can only be a positive integer, and the size of an orbital and its electron energy depends on this n number. Orbitals with the same value of n are said to be in the same principal shell or energy level. And it turns out that the n values are the same as the orbital or the orbit n values that we saw in the Bohr model, where n is equal to 1, n is equal to 2, all the way up to n equal infinity. So those are the n values, and then we have the angular quantum number, angular momentum quantum number, L, which is equal to these 0, 1, 2, 3, and these values basically determine the shapes of the orbitals, which we're going to discuss shortly. So if L is equal to 0, it is referring to an orbital which is known as the s orbital, and that has a particular shape. If L is equal to 1, it refers to the p orbital. If L is equal to 2, it refers to the d orbital. If L is equal to 3, it is referring to the f orbital. Now the possible values of L goes from 0 to n minus 1. Now remember, n is the principal quantum number, right? So the possible values of L can go from 0 to n minus 1. So for example, if n is equal to 2, then there can only be two possible values for L, 0 and 2 minus 1, which is 1. So if n is equal to 2, at that energy level, you can only have two types of orbitals, where L is equal to 0, so that's referring to an s orbital, and when L is equal to 1, that is referring to a p orbital. Each of these orbitals is a different region of space and have different shape. And all orbitals having the same n value and the same value of L are said to belong to the same subshell. So we're going to see how that works out later on. Another type of quantum number is what is known as the magnetic quantum number. And it turns out that the value of ml is dependent on the value of L. Now, the thing about the magnetic quantum number is that it gives some information about the orientation in space of the orbitals. So the possible values of ml are all values from minus L, which is the angular momentum quantum number, to plus L. So if L is equal to 2, then the possible values of ml will be equal to minus 2, minus 1, 0, 1, 2. And each of these numbers represent a separate orbital, right? So if L is equal to 2, at the L equal 2 sublevel, there will be a total of 5 orbitals. Each orbital will be represented by an ml value. All right? So this is basically a summary of the quantum numbers that we have covered so far. So if n is equal to 1, as we said before, L would be equal to 0, and ml would be equal to 0 based on the rules. And therefore, what we're talking about here is a subshell where it comes from the first shell, the n equal 1 shell, and the S is the designation which indicates that we're dealing with an orbital where the L is equal to 0. And the fact that there's only one ml value means that there's only one orbital of that type. Now, when you get into the second shell, or the second energy level, n is equal to 2, there are two possible values of L, 0 and plus 1, or 1 I should say. And then as far as ml is concerned, for L equals 0, there's only one value, 0. But for the second shell where L is equal to 1, there are three possible values of L, or ml, minus 1, 0, plus 1. So what that indicates is that there are three orbitals of the same type within that subshell. Now, because L is equal to 1, the designation of the subshell is P, so you have three 2p orbitals present wherever L is equal to 1. And then you can get into the third shell and use the same argument to rationalize the number of orbitals of the different types present in the third shell. All right, so we're going to talk about that more in class on Thursday. So I want you to make sure that you look at this and understand the rules so that we can take up from there. Now, in terms of the shapes of the orbitals, what you're going to find is that if you plot the wave function squared versus the radius, or the distance from the nucleus, you'll find that this is the plot right here, right? Which, come as no surprise. As you go further and further away from the nucleus, then the probability of finding the electron falls off, right? But if you plot this function here, which basically represents a volume of sphere which incorporates a certain amount of electron density or probability of the electron, you'll find that the plot goes up like this and then comes down, right? And this is oftentimes what we use to represent the shape of the orbital of the electron that is present in that orbital. So as a result of those plots, we come up with the shapes of the different orbitals. Now for the 1s orbital, this is basically the plot, and the resulting shape would be a spherical shape. So basically, in an s orbital, the probability of finding an electron within that region is very high, very high. So therefore, that's the shape of the s orbital. It doesn't matter if it comes from the first shell or the second shell, that's a shape. But the s orbital coming from the second shell has a particular unique feature where you have a region of space right here for which the probability of finding the electron is 0. All right, and when you plot the probability plot versus the distance from the nucleus, you see a maximum there, then it goes down to 0. This is a nodal region where the probability of finding the electron is 0 here, and then the plot increases and the continuum falls off afterwards. And what you find is that as you go from one shell to the next, the higher shell, the number of nodal regions increases, right? So for the third shell, for the 3s orbital, you're going to have 2 nodal regions. For the 4s orbital, you're going to have 3 nodal regions, and so on. As far as the p orbitals are concerned, they are shaped as you can see here. In some textbooks, they call them dumbbell shaped, and the thing about the p orbitals is that they are arranged at mutual right angles to each other. So you have one p orbital aligned along the x-axis here of the 3-dimensional Cartesian system. You have another p orbital that is aligned along the y-axis, and the third p orbital is aligned along the z-axis. So this is what they look like separately. This is what they look like together. All right. So those are the p orbitals. And then as far as the d orbitals are concerned, their shapes are even more complex. This is what they look like separately, 1, 2, 3, 4, 5, and this is what they look like together. At this level, you don't need to know exactly the shapes and the orientations of these, all right? But you do need to remember that there are 5 of them, right? So the d orbitals, they come in sets of 5s. The p orbitals, they comes in sets of 3s, and the s orbitals, they appear singly. Okay. One final quantum number that you need to be aware of is what is known as the magnetic spin quantum number, right? And this spin quantum number was discovered as a result of an experiment that was done by Stern and Gerlach. But basically, the result of that experiment indicates that electrons, their spins are quantized, which means in this case that they spin in opposite directions. So there are only 2 spin directions of electrons. They can spin clockwise around an axis or counterclockwise around the same axis. Now we normally use arrows to indicate the direction of spin. So you might have an arrow pointing up, which indicates that the electron is spinning in one direction, and then you have another arrow pointing down, which indicates that the electrons are spinning in the opposite direction. And the spin quantum numbers representing each spin direction is either plus half or minus half, right? So if plus half represents the electron spinning in one direction for ms, then ms equals minus half indicates the electron spinning in the opposite directions. Okay, so basically those are the 4 spin quantum numbers, right? We have the principal quantum number n, we have the angular momentum quantum number L, and then we have the ml values, and now we just discussed the ms values, all right? So the next class we'll be looking at some assignments where these rules for the different quantum numbers will be used. Now, this is the experiment that was done by Stern and Gerlach, which led to the discovery of the spin quantum numbers. I won't go into it in much detail because, you know, a lot of math would have to be involved, which we're not capable of doing at this level. But basically, silver atoms, a stream of silver atoms was allowed to emerge from this oven, and it passes through a slit, and then it passes through a pair of magnets, and the effect that the magnets have on the beam splits it in 2, and some calculations were done as a result, which led to the discovery of the magnetic spin quantum number, which, as I said before, can only have 2 values, plus half or minus half. Okay, so that's it for this chapter, chapter 7. So the next video will deal with chapter 8.